Science and religion, are they compatible? Does science have the answer for everything? Can it answer all the fundamental questions? Does religion have the answer? Does science deal then with just the physical? And religion is needed for the spiritual or mind? Well, let's see if science has the answer for everything. There was an experiment by Persinger in the Laurentian University in Sudbury, Ontario, Canada. He took a number of students, and unbeknownst to what the experiment was all about, he placed helmets on their heads with magnets to measure their brain waves. Started off using hockey helmets. And then he put them in a chamber devoid of any electromagnetic radiation and any of their senses of sight, sound, and touch. Then he observed what was happening to the brain waves. He found that the left brain was being shut down and the right brain was becoming more active. Then he brought the students out and asked them what they experienced. And 4 out of 5 said they experienced out-of-body experiences. They felt that there was someone beside them or someone behind them. As I say, they could see their body, looked down on their body. Some said they saw demonic creatures. Some that said that they experienced God. So it's been nicknamed the God helmet as a result of that. These same phenomena, though, are experienced by a lot of people with near-death experiences documented. And they seem to be the same no matter what culture, what language, what time. The same sort of phenomenon. One example would be an Australian cyclist. He was going through for the Olympics, and he was hit by a vehicle, knocked out the left side of his body, so he had to have a multitude of operations. And several times he had out-of-body experiences. And he said he didn't really want to come back because it was so beautiful. No pain. And these experiences are common. So is there another realm, if you like, or another domain that, given the chance, your right brain can experience once your left brain allows it to happen? So religion then deals with the spiritual or the mind. If you think that science does, well then ask yourself, if you take you have to go back and prove it in a lab, well, ask them to create a piece of your mind in the lab and see how they make out. But how can religion then be truthful? Because there's so many of them. And do they all say that theirs is the only one? Well, if you look at the fundamental of all the religions or spiritual experiences, no. Fundamentally, they all say that there's something beyond the physical, something that extends beyond their body, something is greater than themselves. And it cannot be described totally by physical characteristics. And you are more than your physical characteristics, of course. You have a mind, you have interpersonal skills, etc. So, of course, depending on how fundamental the religion is, or how dogmatic it is, and if they don't then say that their religion is what they want and only, and nobody else has the truth, then you could say that no, they all have the fundamental, at least fundamentally, have the same concept. Now there are some, excuse me, the most fundamental religion that we know of is the Islamic State. Now they say that their religion should dictate what they think, what they say, what they feel, and if you don't subscribe to that, then you could be punished. Even what you wear. A journalist from the CBC, Canadian Broadcasting Corporation, went over and interviewed a prisoner in Iraq from the Islamic State. And he said, well, if you happen to acknowledge Abraham, you may be given a chance to leave if you don't want to follow their practices. But if you want to stay, you have to follow the practices. And if you don't, you could be eliminated. And if you're a woman under 40, you could be sold into slavery. And they view anybody else that doesn't follow that particular religion, or their version of that religion, as infidels, and who should also be eliminated. And some of the theocracies as well happen to be Islamic. If anyone criticizes them or their leader, then a price is put on their head no matter where they go, and they're trying to be eliminated again. But most of the religions, in the modern world at least, are more tolerant of the different religions. Yes, they have different practices, but they don't necessarily want to say that theirs is the only valid practice, only valid religion. The other religions, especially in the Christian religions, ecumenical movement, acknowledge that there are different branches of the religion that they can tolerate, if not endorse, because they all their similarities are outweigh any of their differences. Now, but you can say, well, what about in the Christian religion, the Jewish religion? The Bible, is the Bible the truth? Well, yes and no. If you think the Bible can describe all the physical characteristics of the world, then maybe it's not. For instance, in the Old Testament, it says the world was created in 7 days. Well, no. Or Noah was able to put all the species of the world and save them all in Noah's Ark. He didn't even mention the plants, I don't think. No. But if you look at the Bible as the truth as far as the spiritual aspect is concerned, use it as a metaphor or as parables, you could say that it's the truth, and it's the truth as far as your spiritual or your mind or your actions are concerned. It may not be able to completely describe all the physical attributes of the world, but its domain is in the spiritual in any case. Now, if you go to the Far East, then, some religions such as Zen Buddhism, they divorce themselves from the physical by a process called transcendental meditation. And by the way, when you perform TM, your brainwaves do change. So are you connecting to the other domain? And many people, even if they don't subscribe to a particular standard religion, still believe in some spirituality, that there is something beyond themselves, beyond the physical. And throughout time, different cultures, different places have always subscribed to that. Even though we now may look at some of them as being superstitious, nevertheless, they still feel that there is something beyond themselves, something beyond the physical. For instance, Columbus sailed the ocean blue in 1492. He came to the Americas and his crew was starving. So he said, "Come on, give us some food," and they refused. Now the Indians believed that at that time, maybe still do, that even the inanimate objects have spirits. So Columbus says that their spirits are angry at them. The moon will be swallowed up in 4 days to show their anger. And when there was a lunar eclipse in 4 days, he got his food. Now we think of that as superstitious, but when we get into science, we'll see things that are really almost as unbelievable as that. And science then really deals with more or less the physical. It tries to break things down. It's a reductionism. It breaks things down to its components and sees how they relate to each other. So it describes your physical attributes, but maybe not your mind or your spiritual attributes. For instance, you are made up of 65% water. That's what you're made. And water is composed of 3 atoms, 2 hydrogen and 1 oxygen, H2O. Now you have other atoms in you too. Carbon, which is important for you because it can combine with other atoms or the other elements in itself to form large molecules. Excuse me, which is important for all complex life like you. Now the atom is composed then of electrons surrounding a nucleus. Negatively charged electrons surrounding the nucleus composed of protons and neutrons. Normally, excuse me, there's as many protons as neutrons and as many electrons as protons. One exception being hydrogen. It has 1 proton and 1 electron. And you are composed mostly of hydrogen. Over 50% of your atoms are hydrogen. Now hydrogen is quite a dynamic element. They used it in airships in the Hindenburg, and it blew up. It's the lightest element. So now they're using helium, the second lightest element. It has 2 protons, 2 neutrons, and 2 electrons. But the size of the nucleus is to the size of the atom as a speck of dust is to the size of a football field. So you all are mostly space. You're virtually all space. You're 99.9999999% space. You're virtually nothing at all. So if you're in a room and nobody seems to hear you or recognize you, maybe that's why. So if you're all space, and your atoms and the floor is all space, why don't you fall through the floor? Because it's virtually all space too. Gravity keeps you grounded. Well, why don't you keep on going then right through the floor to the center of the earth? Well, maybe you're a magician because you levitate 1 angstrom unit, 10 to the minus 10 meters above the floor. You don't actually touch the floor. So what's keeping you from touching the floor and falling through? The electrons in your atoms are negatively charged. The electrons in the floor's atom are negatively charged. Like charges repel. So that's what's keeping you from falling through the floor or walking through the wall or pushing your fingers through your arm. What's it called? The electromagnetic force. Let the force be with you. But your atoms are composed of neutrons and protons. What are they composed of? Well, have you ever had up and down days? Well, you're all up and down. Physically, you're all up and down quarks. Protons have 2 up quarks and 1 down quark, and neutrons have 2 down and 1 up. The up quark has a charge of positive 2/3, the down a charge of minus 1/3. So 2 up and 1 down, plus 2/3, plus 2/3, minus 1/3, or 1, a proton. 2 down and 1 up, minus 1/3, minus 1/3, plus 2/3, 0, a neutron. And those are the smallest bits of matter that we know of. And science has come up with a standard theory of particles. There's 3 levels of pairs of quarks, and you're the up and down. There's also the charm and strange, and top and bottom. The last 2 pairs don't last too long, and you're just up and down. And there's and for each of these, there's a lepton. For the up and down, there's an electron, and for the strong and for the charm and strange, and for the top and bottom, there's the tau and the muon, or muon, I think it is. And there are 4 forces. We talked about 2 of them, or 3 of them. There's a force of gravity, there's a strong force, and there's an electromagnetic force. There's also a weak force. Now, the weak force is important for you as well, because without it, you would die. You are, as a matter of fact, you radiate. You're a radiant person, but not that much. It would take millions of years, millions of billions of years, for your protons to radiate away through radioactive decay. But that radioactive decay keeps the center of the Earth, which is iron, molten. And when the Earth rotates, it sets up an electromagnetic field or shield around the Earth and protects you from harmful solar radiation and harmful cosmic radiation. It also protects the atmosphere from being blown away by solar radiation. And that protects you mitigates at least from you being hit by all the comets, meteorites, meteors, asteroids from outer space, which you don't want to be hit by those either. So let that force be with you. But for each force, there's what is called a boson. for the electromagnetic force, the boson is light, or a particle of light called a photon. So you hold two magnets together, and why don't they touch each other? Well, it's light. It's stopping them from the two south poles or two north poles from touching each of the poles in a magnet. And the force of gravity is a graviton. Until recently, they couldn't find that. And then in the strong force, it's called the gluon. And the weak force is the Z or W boson. But they also figured, a guy called Higgs said, well, there should be another boson and to give mass to all the particles. And he theorized that in the middle of the 20th century. And in 2012, they actually found it. So whenever you have a theory or a hypothesis that predicts something and it comes true, then it gives it more credit. Now, how then do we know all about these particles? Well, science is supposed to be based on observation or on empirical evidence. If you find a piece of evidence that doesn't comply, then you say no. You have to throw out that hypothesis or theory, and or you have to modify it to incorporate that new piece of evidence. Or you have to say that, okay, this theory is okay, but only in certain conditions. So you have to only use it under certain circumstances. And then you really should take it back into the lab and perform an experiment before you can prove it's true. And then have other scientists in other labs also perform the same experiment to corroborate that fact before you can really call it a true theory or a true scientific fact or a law. And can you ever have absolute truth then in science? No. Because you can always say, you should say that it's true so far as the current evidence shows. So it's closer to the truth. But there could be another piece of evidence which happens over and over again that disproves it, so that you have to modify it and discard it, or, as they say, control the conditions in which you're going to use it. Now, how did they come up then with the particle theory? And what lab did they use? Take it back to the lab. Well, they used a Large Hadron Collider, the largest one being in CERN in Switzerland. It consists of powerful electromagnetic magnets in a tube 27, I believe, kilometers along a loop underground in Switzerland, where they accelerate particles near the speed of light, and the speed of light is 10 to the 10th centimeters per second. It's constant. We know that if you look at a planet coming towards you and a planet going away from you, the light from it is the same, and so it's a constant. And then they accelerate particles in the opposite direction, near the speed of light again, and crash them into each other, much like a car roller derby, to see what the parts are going to fly off and what they're made of, the particles. At first, they with so many particles, they called it a particle zoo. But then they came back and summarized it into the particle theory that I just mentioned. The problem being, they were able just to find the Higgs boson, but that was after they increased the power of the collider, Large Hadron. Hadron is anything with mass. Collider. But in order to find the graviton, they would need accelerator, probably the size of the solar system to go back. So what they used there was a wave interference, LIGO or LIGO. And that just happened a couple decades ago, where they were able to find gravitational waves, and hence there must have been a graviton. So they have had some collaboration on finding all these different particles. But hydrogen, where did your hydrogen come from? Well, until 1927, 29, didn't know. People didn't know, scientists didn't know. But then Hubble, looking through the largest telescope on Earth at the time, at the Mount Wilson Observatory in Los Angeles, he saw that all the stars were going away from the Earth. All the stars were receding. What does that mean? It means the universe itself is expanding. And that has a lot of implications. If it's expanding, then it must have come from a smaller and smaller place going back in time. And how far can you go back? Well, if you go back to time equals 0 and measuring how fast it's expanding, you can extrapolate back, and it turns out to be 13.8 billion years ago. Now, 10 years ago, the scientists were saying 13.7 billion years ago. So your scientific facts, don't remain true. Yeah, they must have found a new piece of evidence, and now they've modified it to say 13.8 billion years. But what does it mean when you have no time? Time equals 0. Science cannot answer that question. Closer you can come is Planck, back in the 20th century. He said that you can't keep dividing time down. You start off with 1 billion years, you go to 1 million years, you go to a year, you go to a month, a week, an hour, a day, an hour, a minute, a second, a microsecond, until you get down to 10 to the minus 43 seconds. That's 43 times. And that's as far as you can divide time down. We call it the quanta of time. And we call it the Planck time. It's the time it takes light to travel one Planck length. Planck length is 1.6 times 10 to the minus 35 meters. Another quanta. So what does it mean then when between time equals 0 and time equals first Planck time, if time cannot be divided any lower than that? Again, science has no answer for that. Now in mathematics, when you divide by a smaller and smaller number, you get a larger and larger entity until you divide by 0, and then all hell breaks loose. You get what is called a singularity or infinity. And why? I mean, mathematics breaks down because you multiply infinity by itself and you get infinity. 3 times infinity is equal to infinity. The math just doesn't add up. Well, at time equals 0, you also get a singularity then. And so therefore something as well infinite that creates the finite. The finite is something that has a beginning. Again, science has no definitive answers. Now they may have some speculation or some hypothesis what happens at time equals 0, but they don't have any observation, of course. They haven't produced any universes that I know of. And they don't have any empirical evidence. So it's still just a hypothesis. And you have to be careful because sometimes they use the word theory when they should be saying hypothesis. For a theory to be a true theory, then it should have evidence, observation or evidence. Otherwise, it's just a hypothesis. So here's where you might want to look at the spiritual, the religious side. Because when one talks about God, we talk about someone infinite. And all the powers then, and that first, between the first black time and time equals zero, they say it's a super force, where all the forces are one. Well, again, looking at the religious side of things, you can say there's something there that's omnipotent, all-powerful. And science doesn't have any comeback to that, really, because they don't have any definitive answer to really how the universe started. And then at 10 to the minus the first black time, the force of gravity separates from the superforce. And at 10 to the minus 35 seconds, the strong force separates from the superforce. And at that time, the universe goes through a period of inflation, massively inflation, where it inflates faster than the speed of sound, the speed of light. 10 to the 10th centimeters per second. Now, can things go faster than the speed of light? No, things can't go through space faster than the speed of light, but space itself can expand faster than the speed of light. Then at 10 to the minus 12, you get the electromagnetic force. Separate that. And you also get the weak force, which I've mentioned before. You also get particles and antiparticles created. For every particle, there's an equal and opposite antiparticle. For instance, for the electron, there's a positron. For the up quark, there's an anti-up quark, etc. And when particles and antiparticles come together, they annihilate each other and form energy. So what do you have? Energy and matter interchanging itself? Well, before 1905, scientists said, no, that can't happen. There's a law of conservation of energy, there's a law of conservation of matter. But Einstein, in his special theory of relativity, said, no, they're the same. E equal mc squared. Your energy is equal to your mass times the speed of light times the speed of light. So again, if you get feeling that's so mad you want to explode, don't convert your mass into energy. Because you blow yourself up, everybody in the room, the building you're in, the city you're in. So hold on to your mass, if you don't mind. But at 1/10 of a second, you get protons. But at 1 second, for every billion antiparticles, you get 1,000,000,001 particle. Now, I've heard also 100 million rather than 1,000,000,000. So, again, maybe there's a piece of evidence that had to incorporate, to change the true fact. So that one particle, then 1 in 1,000,000,000 particle, without that you wouldn't be here. Everything is made up of particles. Now, if you had any antiparticles in you, you would explode as well. So you and everything else is because of the particles. One particle is left over 1,000,000,000. after the first second. So there's more things happen in the first second than really the next 13.8 billion years. And science cannot understand that either, cannot explain it. Because when they do take it back and try it, they always get the same number of particles as antiparticles when they convert matter into energy. What's that got to do with your hydrogen, though? Well, for the next 380,000 years, it's still so hot and so dense that the particles can't get together. You've got protons, and you've got photons, and you've got electrons all swirling around. And at 380,000 years after that, it cools down enough so the electron can be captured by the proton. What do you got? One proton and one electron. Hydrogen. So that's where all your hydrogen came from. You are 13, most of your atoms are 13.8 minus 380,000 years old. And you thought you were less than 100 years old. Now at that time as well, the photons were able to be released. And you're still getting hit by those photons. It's called microwave background radiation. And 3% of the static you get in an old TV with an aerial or your AM radio is because of that. It's part of the electromagnetic spectrum, light is, as well as microwaves. But what about all your other atoms? Where did they come from? Well, a guy called Hoyle came up with some good ideas. He also had another proposition or another hypothesis about how the world started, how the universe started, called the steady state theory. He said the universe is steady as it goes, no beginning, no end. There's as many stars there's stars being created and as many stars disappearing. So it's steady as she goes. But when Hubble more or less proved that wasn't the case, he described that case as the Big Bang, derisively, and the name stuck. So the Big Bang theory was given the name by someone who opposed the Big Bang theory. And yet here was a scientist that was very prominent and made a mistake. Some key ideas on how you got the rest of your atoms. So even experts, so-called experts, aren't always right. They should follow the evidence no matter where it leads. So we have all this hydrogen, then what happened to all the hydrogen? Well, gravity brought it all together, a big ball, if you like. Became very, very, at the center, it became through gravity, it became very hot. And if you recall, the reason why you can't fall through the floor, because the space in between, the electromagnetic force, keeping you separated from really touching anything. Well, the mass was so great then at the center that it overcame the electromagnetic charge. And the two protons touched each other, crushed out the space in between them, fused. And when that happened, then it created the next element in the periodic table, helium. Periodic table is how you sort all the different elements, starting from the lightest, hydrogen, going up to the heavier when they add more protons and neutrons. But it also gave off a lot more energy. Like you get in a hydrogen bomb, it's a fusion bomb. And that energy then counteracts the force of gravity. You have the gravity trying to bring everything together, and you have the force of fusion then trying to explode everything and throw it apart. So you have a tug of war between the two. And you also have light and energy given off. What do you got? A star is born. What's the nearest star that you have toward you? Toward yours? Do you know the name? Well, it's the sun. So there it is up in the sky, converting hydrogen to helium and giving off light and heat. A star which is over 10 times more massive than the sun, when it uses up all the hydrogen, converts it into helium, then it takes the helium and converts it into the next element in the periodic table. And so on. But when it gets up to iron, it tries to fuse two iron atoms together. Iron is a heavy element. It doesn't give off energy, it requires extra energy. So there's no energy then counteracting the force of gravity. The star collapses instantaneously almost and blows up in a big supernova. It's creating so much energy, the light from a supernova outshines all the other lights from the stars in the whole galaxy, which could be 100 billion or 200 billion stars. And with all that energy, it's enough to fuse the iron atoms together and most of the heavier elements in the periodic table. So you get your, now all that then is spewed into space, but it does leave behind the core with all those atoms that have no space in them, very heavy, dense, called a neutron star. And 1 teaspoon of that would outweigh all the cars in North America. Again, it would be kind of hard to hold on to the teaspoon. It would be so heavy that this force of gravity would overcome your electromagnetic force in your hand that's trying to keep anything from touching anything. It would fall right through. And it's kind of difficult to count up all the stars as well, all the cars as well. So don't quote me on that. Now a star, which is over 100 times more massive than our star, when it explodes, it leaves behind a black hole. A black hole is so massive that even the photons of light cannot escape. And recently they just figured that in order to get the most heavy elements, it happens when two black holes collide or two neutron stars collide. So you got all this elements and all the material being blown into space. What happens to all that? Well, gravity takes over again and forms a second generation of a star. Our sun is a third or fourth generation, and that was created along with the solar system 4.5 billion years ago. So that's what they said 10 years ago. Now they're saying 4.6 billion years ago. Again, scientific facts can change. Maybe it takes more than 10 years sometimes. So the later elements then, like hydrogen, formed the sun, and the other elements and material was then in a disk floating around, created the whole solar system. First the particles of dust would have been brought together by electrostatic force. And then gravity would have made them bigger and bigger. And they would be very violent at that time. Things would have been bashing together and smashing apart, and then gravity building them up again to bigger and bigger parts until you get planets. And even planets were demolishing themselves. I figured there may be maybe 100 planets, not to mention all the dwarf planets that we still have that people don't really realize. There's probably more dwarf planets in the solar system than there are planets. One of the dwarf planets that we've just demoted to be a dwarf planet is Pluto. But the Earth itself was hit by another planet, probably the size of Mars. It didn't demolish it, but a lot of the Earth's crust was spewed into space and then went around the Earth, and gravity brought together to form our moon. So the moon is part of the Earth. At that time, the Earth would have been molten because of all the bombardment of materials from space. And the moon would have been very close to the Earth. And it would have had material going around it as well. Which is why the other side of the Earth is the crust on the other side of the Earth is I think it's 27 kilometers thicker than the crust on this side. Maybe slightly on the 23 to 27. How do we know that? Well, if you go around the moon, take a trip around the moon, and you'll see there's just the one big lava lake, the one big black spot. Whereas on this side, there's several. Because the crust is cracks in the crust allow the lava to come through and form the lava lakes of a man in the moon. Or if you look from top to bottom, you'll see a man and a female kissing. So maybe that's why the moon is always figured to be romantic. And the moon is important for you because it stabilizes the Earth and allows complex life like you to exist. Without it, it may not be able to. Now the Earth was so hot then for the first billion years or so, and have all that bombardment, that life could not exist. Now how did life start? Science has maybe some hypothesis. They can maybe tell you that you need this component and that component mixed together and so on, but they have not seen it happen, and they cannot produce it in a lab. So they have a speculation or a hypothesis, but not a true theory or a law or a scientific fact. And life, as we know it, at least complex life, as far as we know, only exists on Earth. Now they've been finding, figured at one time at least, that if you went out and looked at other stars, you might find other planets around other stars where life could exist. Something like the Earth does in the Goldilocks position, not too hot and not too cold. So anything out too far out would be all ice, anything too close would be too hot. Now they're finding, and you'd have to have then water, and if it was too hot, the water would evaporate. If too cold, it would just be ice. But now they're finding that even on dwarf planets, there's water. On Ceres, for instance, and Pluto. So it could be possible, even in a solar system, that at least maybe non-complex life could exist. So that's quite a new development. There's more dwarf planets than there are planets. And some of them even have moons on them, one or more. Now Carl Sagan, a great scientist, came up with a few expressions. First, as he said that you are stardust. Not to quibble, but no, most of you before the stars came about. So all but your hydrogen is stardust. So all your other elements then are between 13.8 minus 380,000 and 4.6 billion years old. So you got made up of all sorts of different happenings, where stars exploded, supernovas, or stars created your hydrogen, your oxygen and your carbon. You could have one carbon atom in one finger that's 12 billion years old, and another carbon in another finger that's 6 billion years old. So it created a lot of different happenings before you came about. He also, Carl Sagan, started SETI, Search for Extraterrestrial Information, Intelligence. We put 2 gold plates in the Voyager satellites, one which described the location of the Earth in the universe, and also put on all the different languages, or many different languages of people who spoke on the Earth, so that if any future civilization could find them, they would know at least we existed. And Neil deGrasse Tyson is now narrating a new series of Cosmos. The original Cosmos was with Carl Sagan, and he was inspired by Carl Sagan. And he's a scientist that is very knowledgeable about many scientific phenomena. But life as we know so far is just on Earth, and so that is one of 8 planets, is it now? And several dwarf planets in the solar system. And the solar system is one of 100 billion or 200 billion systems, because we figure each star now, pretty well all stars that we found, have planets surrounding them. And our galaxy is one of 100 million or 2 million galaxies. So a lot of events happen for you to be here. Now life, and when it did come a billion years or so after the Earth solar system cooled down, it would be very simple. One-celled animals, for instance, that would reproduce by just dividing themselves into cloning themselves. It wasn't until you first had sex, at least the sex that we think of today, that things got a little more interesting. The males and the females. That was before, there are forms of life before 500 million years ago. But then you get your half your genes from your biological mother, half from your biological father. And your genes have their cells. And I've heard, I'm not sure, again, if it's who added this all up, but they, you should have more cells in you than there are grains of sand in the earth. Again, don't quote me on that. I'm not sure. And how do you reproduce then? Your cells have a core, and in that core they have deoxyribonucleic acid, DNA. And that gives you your characteristics. Color of your eyes, color of your hair, size of your nose, how big it can get, and how small, how much you're going to weigh, maybe. And the DNA is like a ladder with rungs in it, but it's twisted, so it's called double helix. And when you grow, it splits down the middle, and a new part, another left part comes along and reproduces exactly what the left part is, the right and left part. Except when it doesn't. And then it gets what is called a mutation. Normally, they match each other, left side and right side, exactly. 4 chemicals, which I won't name, I used. But if your DNA changes, your DNA is responsible for your characteristics. So your physical characteristics might change as well when you have a mutation. Now, there are many things that happened in the course of the history of the Earth. Some close calls for life itself. At least 5 major ones, and many more. Life started in the ocean, came up onto the land, formed plants and animals, and they're sort of symbiotic. Plants, by a process called photosynthesis, takes the energy from the sun and the carbon dioxide from the air and produces oxygen as a byproduct. Plants take the oxygen, and by the process I've mentioned with the DNA, and give off, grow and then give off carbon dioxide. So they're sort of in balance. And then when plants die and rot, they get back the carbon dioxide back into the atmosphere. But there's one smart-ass plant. He wanted to capture more sunlight. So he grew taller, so his leaves could gather more sunlight. And when he rotted, or died, he didn't rot. He just lay down and was compressed into coal for millions of years. And then of course during that time, then of course there'd be more oxygen in the air because they didn't get back the carbon dioxide. So the insects at that time would be much bigger because they breathe through tubes, and some of the oxygen is absorbed in the tube. So if there's more oxygen, the tube's going to be bigger and still let the oxygen through. So like a centipede would have been the size of a crocodile. But then at 225 million years ago, in Siberia, I think Siberia and Russia, so hot that lots of volcanoes ignited the coal. And when that burnt up, 70% of all living things became extinct. 90% in the ocean and the rest on the earth. So that was a close call. You had to get through that. Life had to get through that. Then, of course, you had the age of the dinosaurs, 160 million years, where the dinosaurs ruled the earth. Dinosaurs are cold-blooded. and require sunlight in order to move around. Mammals were around then too, but they would have to stay out of the way of the dinosaurs, stay underground during the daytime and come out and eat at night. But during the age of the dinosaurs, the Earth itself was started off as one big continent, Pangaea. Then, during that age, it separated into more or less the continents we have now. Of course, they're still moving, but we don't see it. It's so slow. Now you can speculate or you can hypothesize just by looking at South America and Africa and see that they seem to fit together like the pieces of a crossword puzzle, jigsaw puzzle. But that's just a hypothesis. It took Wagner to get some evidence to support that hypothesis. He looked at fossils on this side of the Atlantic, plant and animal fossils, and looked at the same fossils on the other side of the Atlantic, and found them to be identical species, and only to exist in those places. Then he looked at land. He also, of course, firstly saw that the continents seemed to fit together. That's number one. Number two is the fossils. Number three, he looked at land formations and found they started on one side of the Atlantic and continued on the other. And also the sedimentary rock would match up. And the sedimentary rock has layers of different thicknesses, and they matched up with the sedimentary rock at some places on the other side of the Atlantic. Fourthly, he looked at the fossils in the north and found that they would be only fossils that could have lived in the south. And so the Earth itself must have moved from the south into the north, from the equator into the north. And for that reason, was he heralded as one of the best geologists or scientists of the time? Far from it. He was vilified. He was made the laughingstock of the scientific and geological communities. They said that's preposterous. They ignored the evidence. They let their opinions, the consensus of opinions, override the evidence. And as I say, science should follow the evidence, not the opinions, even of prominent scientists. He died trying to find more evidence in Greenland, and he looking after a couple of people that were stranded in the snow, and he walked off, never to be seen again, not knowing that his theory, and you can call it a theory because it has the evidence, would be vindicated. It remained several decades later till another scientist came up with the explanation of how that could happen. The continental drift theory, where the Earth's crust floats on top of the magma in the mantle, and plates, and moves around on those plates. And when the plates meet each other, or one goes under the other, you get all sorts of volcanic activity and earthquakes and so on. And I say it's the continental drift theory, which is now accepted. So science can make colossal mistakes, and in one sense, it is based on mistakes. You have an hypothesis, and you have to prove whether it's true or false. And often, with new evidence, you have to say it's no longer true. And the new evidence supplants the old. Now, at 65 million years ago then, there was another catastrophe, at least as far as the dinosaurs are concerned. Because Jupiter, which is the larger than all the other planets combined, and hence has the greatest force of gravity, attraction, would attract a lot of the debris, the meteorites, the comets, asteroids, meteors, and so they couldn't, to avoid them from hitting Earth. But it let through a big whopper 65 million years ago, and it was so big it even got through the Earth's atmosphere and landed in the Yucatan Peninsula in Mexico. Really caused a lot of problems. Spewed up a lot of material into space and burnt off a lot of the vegetation because there was so much energy caused so much heat that it circled all that circled the Earth and blocked the sunlight from coming down. And as I say, dinosaurs, which require sunlight in order to move, became extinct. They also eat large amount of vegetation. So that allowed the mammals to come out from underground in the daytime, and they proliferated and took over all the niches formerly held by the dinosaurs. Now 10 million years ago, the South America and North America came together. Before that they were separate continents. Still are, but they're joined. That created a different ocean currents, and that meant the climate of Africa changed. They could not support the number of trees it did before, so grasslands sprung up, and trees became very crowded. So they decided to go down onto the grassland. And as luck would have it, they probably got bombarded with some cosmic rays, which changed their DNA, and those who had the DNA changed so that their characteristics could better survive in the grassland, went on, survived, and passed on their DNA to their offspring. And the next is history. So you are here because a lot of different events have happened. Your parents had to meet, and they had to produce you. And your DNA is half theirs, half of each of those. And their parents, their grandparents, had to meet, and you are then 1/4 of your DNA comes from that. Over 100 years, say 4 generations, 16 different. You have 16 different people's DNA. Over 1 billion years, 16,000. And as I say, you come from one planet in one solar system, from 100 billion planets in the galaxy, or more, from 100 to 200 billion galaxies. And then you had 1 billion to 1 chance of making it through after the first second, when the particles outweighed the antiparticles. Then you have the first second, you have your force of gravity keeps you on the Earth. The electromagnetic force keeps you from falling through the Earth. Strong force keeps you from falling apart. And the weak force that protects you from all the harmful solar radiation, cosmic radiation, and materials from outer space, and protects the atmosphere, which you need as well. So it looks like it's pretty miraculous that you were able to exist, and why you're here. I'm going to stop here and continue.